I'm going to break you out of this habit of staying silent sometime, somehow. What do you take aromatic to mean? It means nothing. You've never heard it used outside of this classroom. The aromatic ring. That's all you know aromatic means? No? You don't like aromatic perfumes?
I wear perfume, but I've never...
You don't go for the perfume for their aromatics, for their smells?
Yeah, I do.
Oh, you do? But you didn't use that word in that sense. Is that what you mean? You guys heard it used that way, or am I introducing you to a new vocab?
Is it like aroma? Like I've heard it.
Aroma, yeah.
Okay.
Yeah, things that are aromatic have a good aroma. I would say pretty much just that. Things that have aromatic rings are considered aromatic, but not everything that has an aroma has an aromatic ring. So there is this double usage of the word aromatics. We say aromatics as in those things that smell good, and we say aromatics as in those things with aromaticity. And aromaticity is this physical property, and it governs some of the chemical properties. What I like to define aromaticity as is a stabilizing electronic force, or phenomenon, maybe. You guys have heard me refer to certain things as being a stabilizing force. And usually I'm talking about resonance. Resonance is something that stabilizes a charge, stabilizes a radical. Resonance and the conjugation of pi systems is stabilizing. And so aromaticity involves resonance to a certain extent, but in ways that are distinct from all of the other ways that we've seen resonance. To demonstrate the resonance, I want to start off with some nomenclature. The nomenclature of benzene. So actually, it's kind of cool. In Arabic, benzene is the word that they use for fuel. Like you go fill up with gas at the gas station. In Arabic, you would say you fill up with benzene. And then again, the Arab world laid the foundation for chemistry. So there's a lot of overlaps. Benzene itself is not a compound that we will work with all that much, except for maybe as a starting material. But now let's consider a derivative of benzene. This molecule is called xylene. It's actually one of the three possible structural isomers of xylene. And I want to try and prove that these are the same, but I also want to prove to you that they look like they should be different. So to prove that they are the same is important. If we were to give benzene an IUPAC name following all of the same systems that we already use, it's a 6-membered ring, so it would get the parent chain cyclohex. You're welcome. It's a trialkene, or at least it looks like a trialkene. So we would call it cyclohexatriene. And when we name alkenes in a ring, we start at one of the positions of the alkenes and count through the carbon-carbon double bond. And we'll do that in such a way that we can minimize the lowest locant set, which means lowest at the first point of difference, not necessarily lowest total. So if I were to name using like IUPAC nomenclature, if I were to name the resonance form of xylene on the left, what locants would I give to my methyl groups? Good morning. 1 and 2, that's the lowest possible locant set. If I start on one of the carbons that has a methyl group, I'm starting at a carbon of the alkene, so I need to count through that carbon of the alkene. We would maybe call this 1,2-dimethyl. Oh, I forgot the dimethyl. 1,2-dimethyl cyclohexatriene. Any arguments against that? Good morning. Do you agree? If we were following classic IUPAC nomenclature, the stuff that you learned in OChem 1, unless you learned how to name aromatics in OChem 1, this would be the most appropriate name for it. And for the derivative on the right, not the derivative, the form on the right, what would we call it? 2,3 is not the lowest possible locant set. So the way that you numbered that was perhaps to start here and number around. So you've given the two methyl groups position 2 and 3, but there's a way to put a methyl group on carbon 1. And that would be a lower locant set at the first point of difference. This is 2, 3. But if I number it here in green, I can get a methyl group to start on position 1, but I have to count through the alkene. So I go counterclockwise, which means that I get a locant set of 1, 6, which is a lower locant set at the first point of difference. That's the most important rule about nomenclature locant sets, is that you give the lowest set at the first point of difference, and 1 is lower than 3, so this would be called 1,6-dimethyl cyclohexatriene. When aromaticity was being sussed out, when the aromatic ring's properties were being determined, it was reasoned that these should be 2 structural isomers. The pi bonds are isolated in different places, correct? If the pi bonds are isolated in different places, then the nature of these alkenes are different. Take, for example, a tri-substituted alkene and a tri-substituted alkene versus a tetra-substituted alkene. Their chemical properties should be different. They may have some different physical properties. They may have very similar physical properties. But before we understood aromaticity, this was predicted to be 2 different structures. Now we understand xylene to be some resonance hybrid of that. So we call it 1,2-dimethyl benzene. There is no cyclohexatriene. Because if there is one cyclohexatriene, then there must be another cyclohexatriene. And if there are 2 different cyclohexatrienes, then they should have different physical and different chemical properties. And they don't. They can't be separated out. They can't be selected based on their reactivity. They are not different compounds. They are resonance forms of the same. And so we introduce this circle. And the circle tells us that it's not a double bond in some places and a single bond in others. It's actually a 1.5 bond all the way around. It's never the structure on the left and the structure on the right, or then the structure on the right. It is never these structures. These structures fail to isolate exactly the nature of the aromatic ring. This one does a better job, but there is a limitation. Can you think of what limitations drawing a structure like this has?
When doing matching, you can't locate a single bond, I guess?
Yeah. Actually, I like this. If you're going to show a bond breaking, you need to have an arrow that starts from that bond. How can you designate which of, there must be something like 3 bond character in here, but how can you isolate where a specific bond would be? Good point. Anything else? Other limitations that you guys? I'm not trying to hit at something in particular. I'll share the big limitation that I think of, but I am curious what you guys see as the biggest limitation here too. And I like this Salsabil. In fact, when I have you guys draw mechanisms, you're allowed to put a circle in unless you have to show a bond breaking, because this doesn't clarify which bond you're trying to indicate breaking. How many pi electrons in this structure? Is that a hard question? Okay, then answer it. How many pi electrons? It is a hard question. What are you doubting? No, getting ahead of yourself. How many pi electrons? I love this. 6 pi electrons. Count the double bonds, right? The double bonds are the only pi bonds here, and there's 3 of them, so there's 2, 4, 6 pi electrons. Great. It's obvious because we counted the double bonds. How many pi electrons here? You know the answer is 6, but there's no way to infer that from this drawing. How could you know? It's another assumption that you have to make. You now have to assume that these make 6 pi electrons. And I'm going to say specifically just this one because there are other structures that you guys will need to get familiar with that use circles but do not indicate 6 pi electrons, and that's where Salsabil is coming from with the 4n plus 2 rule we'll talk about. But not every circle means 6 pi electrons. In practice, you have to memorize that the circle means aromatic and aromaticity has a specific nomenclature to it. Okay, before I get further into what is aromaticity exactly, I want to talk a little bit more about the nomenclature of benzene. At the top of your handout, you've got a series of mono-substituted benzenes, and I'm going to give you the IUPAC and common name if they have a common name. But I'm also going to give you guys a task with some of those structures at the top. I'm going to make you devise a new compound, a polysubstituted benzene, and then swap it with somebody else to be named. So I want to talk first about the unique aspect of benzene's nomenclature. We know that when numbering locants in a ring, there's a lot of freedom in where you start. You typically start at where the highest priority group is, or where you're going to get the lowest locant set. And with benzene, we find that positions like 1 and 2 become even less meaningful because these groups aren't necessarily on either side of an alkene or anything. They're just on the ring. So for di-substituted groups or di-substituted rings, we get these new terms ortho, meta, and para. Which can be used to substitute the locant positions. 1, 2 tells us about an ortho-substituted group, 1, 3 meta, 1, 4 para. And so in any place that we would have taken 1, 2 dimethyl, for instance, we can say ortho-xylene or ortho-dimethylbenzene. There's orthoxylene, metaxylene, and paraxylene, the three structural isomers of placing 2 double bonds across. If it's just one group in the ring, of course, we don't have to say the location on it of that group. But if one of those 2 groups changes the suffix for benzene, then that should be the priority group, and it will always be assumed to be position 1. And then other groups that are relative to this suffix changing functional group, they can just be described in the prefix with their locational term. So let's go through some of those IUPAC names and common names for the compounds that you have at the top. I think that you guys can help me a lot with the common names. What would be an appropriate common name for this first structure? Not common name, sorry, IUPAC name, systematic name. Our root, our parent chain is benzene, and the substituent on this one is methyl. So this is methylbenzene. But its common name is toluene. Okay, a deal that I'll make with you. I will never require you to know the common name. I may use the common name more frequently than its IUPAC name, but if I ever give a question where you're graded on naming it, then you will be able to name it using its systematic name. Toluene is really the only way that you'll ever hear this compound referred to, but anyone that hears you say methylbenzene will absolutely understand where you're coming from. Okay, the next one, its systematic name is maybe not one that you're familiar with, naming that carbonyl group that comes off, but this is just a vinyl group, so this is called vinyl benzene. And its IUPAC name is styrene. I'm sorry, I keep flipping IUPAC in common. Can you hear from that common name? This is a precursor to a popular plastic. Styrofoam. Yeah, this is your precursor to styrofoam. All right. Then we have cyanobenzene. Cyanobenzene, to my knowledge, doesn't have a very common name. It's really only its systematic name. The other two, it depends on how you look at it. I'm going to say that these other two have a more common name than systematic name because the name that we use for these two is quite different than how we name most other aldehydes and carboxylic acids. The first compound is called benzaldehyde. I wanted to introduce you to a new way of drawing benzaldehyde, but you can redraw this if you'd like, showing that CO double bond structure. I just want you to be familiar this semester with how aldehydes are abbreviated. We abbreviate aldehydes as CHO. Most of the time when we name aldehydes, the suffix gets tacked on AL at the end, but we don't tack on aldehyde at the end of most compounds' names. So benzaldehyde is unique in that. And similarly with benzoic acid, you'll never really see a way of describing the carboxylic acid as a substituent. Rather, we just suffix the whole last name, or the whole last part of the name, in a way that we don't suffix most. Also, I think it's kind of funny, benzene sounds like it has an alkene in it, but no alkenes. Aromatics are not alkenes. Okay, this last one is also very similar to these other two, but I did give a generic form so that R group could be substituted for methyl, ethyl, tert, butyl, phenyl, anything. This is an alkyl benzoate. And whatever you want to swap that R group for, that R group gets swapped for. All right, the next three do not have common names, only systematic. So I'd like for you to please tell me what they are. These should be straightforward enough. Chlorobenzene. Mimi got one. Who's got the next? Bromobenzene. And the last one? Nitrobenzene. I'm going to skip to this very last one. This is sulfonyl benzene. What we have on the structure is a sulfonyl group, 2 SO double bonds, and then an SOH. But these last three have both systematic nomenclature and common nomenclature. Systematic nomenclature tells us that an NH2 group is aminobenzene. An OH group is hydroxybenzene. What would be the systematic nomenclature for an OCH3, an ether group? I mean, think about how I have hydroxy, but I'm swapping out the H for a methyl group. Methoxy. Methoxybenzene. The common names for these, things that you may have already seen in lab if you did the methyl orange lab last week. Aniline, we actually used a substituted version of it, dimethyl aniline, phenol, and anisole. And I believe the structure of anisole is related to, or the structure of anise, or anise oil, is related to anisole. Has that methoxy group in it, I believe. Okay, so here's your task. Individually, I want you to make one structure. That could be a di, tri, tetra, penta, or hexa substituted benzene. So it should have somewhere between 2 to 6 groups. Then swap with someone and name their compound. So I'm not saying you have to name yours necessarily, but you've got to name someone's. So I'll give you an example. I'm going to take benzene with 4 groups, and I'm going to put 3 nitro groups around the ring and 1 methyl group right in the middle. And I'm going to refer to this as a toluene compound. I could call it methyl, but I'm going to say that this is toluene. Because I've decided that this is toluene, the carbon that makes it toluene becomes carbon 1. Methyl is not a higher priority substituent than nitro. So if I were naming this as methyl and nitro, I would look for the lowest possible locant set everywhere. But because I'm naming it as toluene, this becomes carbon 1. So I have 1, 4, 6 trinitro toluene, also referred to as TNT. If I wanted to name this using the common nomenclature, then I would look for the lowest possible locant set, and I would have 1, 3, 5. Well, let's see, actually, LMNNOP. 2-methyl, 1, 3, 5 trinitro benzene. Both acceptable answers. Both correct answers. Both correct names for it. Just depends on whether you want to get more familiar with common names or systematic names, and I would encourage you to do both. Be familiar with both. All right, take about 5 minutes to make sure that you have a compound. Swap with a neighbor and work on naming each other's compounds. In 10 minutes, I'll pull us all back together. It shouldn't be 146, sorry. Oh, thanks for saying that. What should it be? No, it should be 2. Because if I'm calling this toluene, yeah, did you guys catch that mistake too? If I'm calling this toluene, the methyl group is at position 1. I've said this is not just a benzene ring, it's a benzene ring with a methyl, toluene. Therefore, I have to start here. Because of that, my nitro groups were at 246, not 146. Sorry.
No, that's okay. I was like, where are you starting off from? And where are you counting from?
And down here, I am going for the lowest locant set, so 135 for the nitros. And I'm still alphabetizing by M and N. Nitro just comes after M.
If you wanted to do like the first version,
Yeah.
can you use the systematic
Right, okay, so, wait. Sorry, what do you mean?
Instead of using toluene, using methylbenzene.
Yeah, I can. I just have to.
You have to do it like that, though. You can't say like 2,4,6 methylbenzene.
Right, because 2,4,6, 1-methyl 2,4,6 trinitro is a worse locant set. 1, 2, 3, 5, versus if I started from here, I'd get 1, 2, 4, 6. So I'm going to go with the lowest possible locant set, which would mean getting all of these right next to each other. Good question. Depending on whether you make methyl a part of the root or a substituent changes what locant set you want. Oh, and why am I not allowed to use orthometa-para? More than 2 substituents. If there's more than 2 substituents, you can't do it. You are not allowed to use orthometa-para. For instance, I've had students that try to take this, call it toluene, and then call it di-ortho-para-trinitro-toluene, right? To try and describe, oh, I've got 2 groups that are ortho, 1 group that's para to the toluene position. It's too far. More than 2 groups, these rules break down. So only use those if you draw di-substituted. I see a couple of switching. You guys are still working on your drawings then?
So we have 2 like potential parents.
Yeah.
Which one, do we choose the first one based on which one gives the lowest locant, or is it alphabetical?
No, so in your case, you could either make the benzene ring toluene or styrene.
Okay.
You've got both options.
Okay.
If you call it styrene, you're going to have to describe methyl as a substituent. If you call it toluene, you'll have to describe vinyl as a substituent.
Okay. That's what I was confused about. 'Cause I was like, okay, it's good to know.
Yeah, you get the choice. Oh, which is why I would avoid using benzaldehyde and benzoic acid in the same structure, because I haven't shown you how to call the benzaldehyde group a derivative or a substituent. And in my opinion, it's just more work than it's worth. But we can go over it.
Because that one you'd have to use the first way, right? I mean, like if you use either of those, because we don't know those.
Can you remind me your name? Yeah, man. Okay. I'm going to have you and Evan trade off once you're both done, okay? Great.
Which like better though?
I don't know why I was thinking you were in my OChem 1. I'm having a really hard time keeping them separate this summer. So when I saw you, I was like, it looks like Yemen, but he's in my OChem 1. He wouldn't be in here. No. Okay. Great to meet you. Welcome back. Tell me.
Would it be like 2-fluoro because this would be primary? It's like similar to the rule of alcohol. So this would be primary group, and then this would be so 2-fluoro and like 1, 2, 3, 4. So that'd be 4.
Correct. And then E comes before F. So we'll write 4-ethyl.
2-fluoro.
Yep.
Okay.
But you did that exactly right with anisole.
Hey, get your own work.
Yeah.
Yikes.
Don't cheat off of ours.
Yikes. Okay, deal. I won't cheat. I'll be right back. I've already been burned too much.
You got another structure.
No, that's good. You can go with that.
Sorry, we didn't mean to burn our Well, I didn't mean to burn our
So if you're doing benzaldehyde or benzoic acid, that would have to, you'd have to use it the first way. naming it?
What do you? Oh yeah,
Or
like
using the common
yeah.
one or whatever.
so. Let's say you wanted to have an aldehyde group and a carboxylic acid group coming off the ring.
Okay.
You
Well,
could
not even that.
you
just
could
like
call
in
it
general.
carbaldehyde benzoic acid. Carbaldehyde is the name
That's
for an
scary.
aldehyde being a substituent,
Okay, carbaldehyde.
right? Like carb for like carbon,
Okay.
like carbocation, carbanion, carbaldehyde.
Okay, so what if you had just like a methyl group and an aldehyde? Could you still name it off of carbaldehyde, or would you just use benzaldehyde?
I would just call it a methyl benzaldehyde,
Okay.
but you could call it carbaldehyde toluene. I just don't think anybody would do that.
They
I
might
think-
point and laugh at you.
Yeah. Maybe they wouldn't point and laugh, but they'd be laughing on the inside. Absolutely.
Okay.
And this is good, but no hyphens.
Oh no.
Hyphens only separate the locant positions.
Is that?
I mean, the M, I guess, yeah. The M should have a
And that's just
hyphen?
One word.
but it's all one word, yeah.
I hate that.
Bromochloro. I mean, you've heard of chlorofluorocarbons, CFCs,
Yeah.
like destroyed the ozone layer. That's all one word, chlorofluorocarbons. Yeah, we love shoving stuff together. Sorry, Evan. What you got?
So this was first kind of like wrote a different orientation, but
Mm-hmm.
does that work for that? Like using this as one?
So, because vinyl benzene has a common name.
Right. So styrene would be better?
So if you want to use the vinyl substituent as position 1, then we have to name the ring based off of,
Oh, then it has to be the styrene.
then it has to be styrene. This is close, but V comes after M. So it would still be 3,4-dimethyl, 1 vinyl benzene. And Evan, that's the other thing about yours is you could keep vinyl, but then you'd have to give it a locant as well.
So it'd have to be like one, oh, it actually would come after. Huh? So it'd be like 3, 4.
And now, Jaylee, before you leave that one, your locant set is 1, 3, 4, but you could have a locant set of 1, 2, 4. And 2 is lower than 3, so our point of difference. Yep. Right. Yes, but your locant set is 1, 3, 4 instead of 1, 2, 4. So your lower locant set will be 1, 2, 4.
I don't know if I don't think this is going to
Are you saying both the methyl and the bromine are coming off of position 1? 1 methyl, 2, 1 bromo?
That's not.
So if this is position 1,
Yeah.
then this becomes position 2 and 6.
So 2, 6.
2, 6. And we add multipliers to suggest how many of those groups we have. So it would be 2, 6 dibromo.
Diprom.
Now, before you make all these little changes, you haven't added the chlorine in.
Okay.
So somewhere in your name, chloro is going to have to come in.
Does it have to say 1 chloro?
Well, depending on its position. If you're starting here, then the chlorine is at position
Okay.
4. And the groups have to go alphabetical. So it would go bromo, chloro, methyl, benzene. Does that make sense?
Yes, it is.
And then the last thing is, if you're choosing to start here, your locant set is 1, 2, 4, 6. But if you started here, you could get a locant set of 1, 2, 3, 5,
Okay.
which is a lower locant set. It's what I have in blue circled there, 1, 2, 3, 5 versus 1, 2, 4, 6. We want the lower locant set at the first point of difference. And either of those locant sets give you 1, 2, but the lower locant set has 3 instead of 4. If you wanted to start numbering at position 1 where the methyl is, then you can't call it benzene, and you wouldn't refer to the methyl, you'd call it toluene, and you would assume the methyl with the benzene. See the difference? Great. Could I get some examples to put up on the board?
Yes.
Tell me.
Do you want the name?
Good question. Why don't I do this? Why don't I take two names and take two drawings so that we can see how to name them and how to draw them? Jordan, which one do you want to give me? A name or a drawing?
Drawing.
Okay.
There's, well, I don't know how to tell you without.
Well, you can still use those terms like put a methyl with an a nitrogen group. Put a benzoic acid with a.
What about benzaldehyde?
Okay.
And then one away.
Ortho.
Yeah, sure. Yep. Is an OH.
Good.
And then two more away. What would that be?
Para to the benzaldehyde.
Yep. Is a methyl.
Great. Good. Can I get another structure that we can name together? Preferably a dye substituted. I think you guys went above and beyond. I didn't see a lot of dye substituted. Yeah? Can I get one of yours?
Yeah. So just on whichever one, put a chlorine,
Yep.
and then move over. Yeah, right there, bromine.
Great. Okay.
I think I went too far. Sorry.
Well, that's okay. If you're all right with that. Then can I get two names and we'll draw them based on the name? And these can be whatever substituents. Salsabil? 4-ethyl, 2-fluoroanisole. And one more?
That looks scary.
No, it's really not. Quana or Quan Cao, you guys got one I could write up here? Okay. Do you have numbers or a letter in there? Ortho dihydroxybenzene. Awesome. All right. I'm glad that you gave me one that was orthometapara so that we can practice using that nomenclature. So top left, all three of my substituents could give the benzene a common name. I could call this a hydroxycarbaldehyde substituted toluene. I could call it a methyl carbaldehyde substituted phenol, or I could call it a hydroxymethyl substituted benzaldehyde. I'm going to go with benzaldehyde as the root because I think it's far less common to see the aldehyde as the substituent. Part of that reason is that aldehyde is a higher priority functional group. But the odd thing here also is that the aldehyde comes off of the chain. So it's a strange group to name otherwise. So I'm going to name this as benzaldehyde. Because of that, my position 1 is at the benzaldehyde carbon. And for no other reason other than I chose it to be, because I'm naming it benzaldehyde. If I decided to call this phenyl, it would have been at the carbon 1 would have been at the alcohol. If I decided to call this toluene, carbon 1 would have been at the methyl group. This is another place where it can seem easy to say it's an orthohydroxy paramethyl benzaldehyde, right? Couldn't those location descriptors, O, M, and P, couldn't they just be applied as needed? Honestly, I think maybe they could, but we won't. Because I've got more than two groups, we're limited here, and we'll call this a 1-hydroxy 4-methyl benzaldehyde. I don't know why I keep doing that. I'm literally numbering my carbon 1 and then adjacent to it, giving the wrong locant. You guys got any tips? Is it just my 8 a.m. brain? Okay.
I kept skipping substituents.
That's a silly mistake. That's what I would describe it as. That would have lost like some small partial credit on an exam. I don't know why I keep doing that though. Twice in one day is more often than normal for me. All right, now for this next one, there is no common name that I can use. So both bromo and chloro will just be named in the substituent. If I wanted to use locants, I need to give a locant to each group. Well, obviously one is going to be 1, one is going to be 4. And it would be tied either way. So how would I decide which locant goes to which substituent? A tie goes to the alphabetical. So I would name this 1 bromo, 4 chloro, benzene. Notice how each group gets its own locant. It's not 1,4 bromo-chloro. It's just like normal. Bromo's at position 1, chloro's at position 4. But if I don't want to use 1 and 4, then I can call it para-bromo-chlorobenzene. I don't need to say bromo is at 1, chloro is at 4. I can just say that the two groups themselves are para to each other.
Does this have any, like, you know how like alcohol is a higher priority when you're doing other nomenclature? If one of them was an alcohol, would it matter or no?
No. Well, yeah, even if this was an OH instead of Cl,
Yeah.
that would just be para-bromo-phenol
Okay.
or para-bromohydroxybenzene. You've got two substituents. They are either ortho, meta, or para to each other. So you can just put two substituents into the name and say that they're related, ortho, meta, or para. It would be wrong to say 1,4 bromo-chloro. That would be wrong. If you're going to use locants, assign the locants. But if you're going to use ortho, meta, para, that just goes out front regardless because neither of them take higher priority. I guess if we were going to do this, I think we'd have to start at hydroxy and we'd have to say 4 bromo, 1 hydroxy. But we can generally we can avoid that by having these higher priority groups, by having the common names, excuse me. All right, down below, let's draw it out. I'm going to start with the parent chain. So I'm starting here with anisole. Any tips on how to remember anisole? I don't have any. Luckily though, you're not tested on whether you remember anisole or not. I sprinkle those into my exams. You will see common names, but at no point should the common name be the limiting factor on whether you earn the point or not. A lot of times I put them in there as ways for you to learn more about a structure, not necessarily to test you on it. There's anisole, so obviously that's position 1, and then position 2 could be on either side. I've got a fluorine, and then position 4, an ethyl. Great work. And Salsabil fell into the same trap that I did by referring to the fluoro as position 1? No.
I did originally 2 fluoro ethyl.
Oh, the ethyl was at 3 instead, right. All right, now for this last one, I've got 2 hydroxy groups, and they are ortho to each other. This has another name, actually. This has a common name. I think it's like catechol. And I'm not going to introduce that common name on the board because I don't know how to spell it. How else could we have named this instead of ortho-dihydroxybenzene? 1,2-dihydroxybenzene. What else?
Can you still do ortho? Phenol. I know that would be there.
If I wanted to use phenol, how would I describe the other alcohol? I could say 2-hydroxyphenol, because phenol would claim this as position 1 and the other hydroxy is at position 2 relative to it. So 2-hydroxyphenol or ortho, O-hydroxyphenol. Yeah, so I can refer to both of them or just one when I name them in the substituent. Okay, I want to show you guys some cool ones. Ones that I'm not necessarily going to ever show you again or make you name, but I do think that they are interesting. A lot of them have to do with toluene. This is toluic acid. That makes a lot of sense, right? Although it's one of the 3 possible structural isomers of toluic acid. Which one isomer is this exactly? Orthotoluic acid. Do you notice how in that name, orthotoluic acid, there is so little information about what's going on? You have to recognize that toluene has been substituted, or that toluene has been derivatized. It's not toluene anymore, it's toluic acid. Another one that I think is quite fun is one that you guys have actually already used, most likely, in OChem 1. This is called toslic acid. You guys maybe have used tosylate or tosyl chloride, and that TS part is representing this. Although specifically this is para-toslic acid, and you can hear in the tosylic part that they're trying to tell you there's a sulfonyl group. So cool. I think that's all that I think are really interesting for now. In lab, in a few weeks, you'll see other derivatives of benzene that are used. In fact, toluic acid will be one of them, and you'll end with a toluamide. So we don't have to stop just at the common names themselves. We can take the common names further. Okay, I think that we'll actually get into understanding more about what is this stabilizing force of aromaticity tomorrow. And what we'll use the rest of our time to do is look over reactions that are significant to benzene, or really the benzylic position. So to introduce these reactions, I want to introduce you to some regio terminology around benzene. When we describe the carbons of and around benzene, we have aryl carbons. Those are the carbons of benzene. They are aryl. And you can hear how aryl is related to aromatic. The benzene group as a whole is called phenyl, which could definitely be confused for what? Phenyl. Spoken, it's quite hard to tell the difference between phenol and phenyl. But the benzene group as a derivative is a phen group. So that YL suffix just tells you that you're looking at a substituent. Here the substituent is benzene, so it's a phenyl substituent. The carbon off of, I'm going to do this in a different color. The carbon off of the aromatic ring, do you know what? I'm going to do this on a whole other example. The carbon off of the aromatic ring is called the benzylic carbon. In this case, I have a benzylic CH2, unless R is hydrogen, in which case I have a benzylic CH3. But benzylic just refers to the carbon off of the ring. And this group, including the benzylic carbon, this group is called benzyl. Easy enough, right? If benzene is the substituent, call it phenyl. If benzene plus something is the substituent, call it benzyl. I don't know. They probably could have been a little bit smarter about what terms they applied here. So don't mess it up. So here's a good example of both of these terms being used in nomenclature. Wow, that was a great. And actually, I'm gonna abbreviate these differently. I'm gonna show you that we can abbreviate benzene as pH, which of course stands for phenyl. So this is an ether. This is a benzyl phenyl ether. You can see how the two sides are connected, right? Benzyl phenyl. I can't stress enough that the reactions we're doing are benzylic reactions. At the end of this week and next week, we'll be talking about reactions at the aryl carbons. But for now, we're looking at reactions at the benzylic carbons. So we're looking at reactions that are moderated because of the aromatic ring. The aromatic ring changes the properties of the benzylic carbon and allows the benzylic carbon to go through these reactions. With the exception of the last one, which is not benzylic specific, but is significant to the benzylic reactions, as we'll learn next week. So I am still testing out how best to make use of these worksheets. So what I've done this time, in the past I've given the reactions on the left as just starting materials and arrows, and then had you fill in what's missing. But here I'm actually showing you everything, so you should be able to apply it to what's on the right. My printer really did me dirty and did not print this part of the document well. So you may need to look this up on Canvas or look up here to be able to copy it down and know what it's asking you for. But I've given you two different syntheses, two different roadmaps really. One is more like a synthesis. You need to be able to track how the structure changes. The other is more like a roadmap where you just need to apply reactions. Here's the deal. I still don't feel good about just giving you this and letting you run wild with it. I think what I'll do instead is name these reactions and give you some important pieces of information so that you can have that as a separate piece to just all the data. Oh, there's another thing I wanted to mention about abbreviating with pH. pH only means benzene. The only thing coming off of that group is the rest of the aromatic ring. So if, for example, you had a substituted benzene that you were trying to show in this same way, there's no way for you to use the the pH derivative, yeah? Because is that ortho, meta, or substituted bromine relative to the ether? No clue. So you're allowed to use pH to abbreviate the ring when the only thing present is the ring. If there's a lot else going on, you can't abbreviate using pH anymore because we can't communicate what the orientation, what the structural relationship is of those other groups. Okay, so our first reaction is a review. This is HX addition. I think I should have paired this with acid catalyzed hydration, which have in common a carbocation intermediate. So whether you're doing HX addition or acid catalyzed hydration, just like in the OChem 1 review mechanisms, they're essentially the same process. It just differs what your nucleophile is. Remember that in these reactions, it is the most stable carbocation that forms. What was our rule about carbocation stability in the past? The most stable is the most substituted. So if this is a methyl carbocation, and here is a tertiary carbocation, primary and secondary carbons fall in the middle. But as it turns out, it's not just the most substituted that makes it the most stable. What's more stable than this is a primary, secondary, or tertiary allylic carbocation. Why? The resonance stabilizes the carbocation. And what's more stable than an allylic carbocation is a primary, secondary, or tertiary benzylic carbocation. Which means that the benzylic carbocation must have more resonance than the allylic carbocation, because more resonance is more stabilizing. And I want to demonstrate for you guys what some of that looks like. We'll actually look at the example that we have in this reaction. Please keep in mind that when you draw in the double bonds of the aromatic ring, it doesn't really need to be in the sequence that it's drawn, because neither resonance form even exists. It is very possible that one resonance form is easier to draw than the other. I have a benzylic carbocation, which means electrons can flow from the ring to that benzylic position. This group has just withdrawn electrons from the ring and left in its wake a positive charge in the ring. And now more pi electrons within the ring can keep moving around keep delocalizing the charge. Oh, but don't forget, these don't exist. If any of them exists at one time, they all exist at one time. So it's not that the positive charge is moving around the ring. It's not that the electrons are being pulled out of the ring. That positive charge is in each of those positions all the time. despite that fact that this positive charge moves around the ring, the final product isn't where the halide adds to any of those positions. The final product is when the halide adds to the benzylic position. This actually tells us there's something special about the aromatic ring. Despite the fact that it can move electrons around and it can take on this positive charge, that positive charge is never attacked inside the ring. The ring is always reformed before the end of the reaction. So I gave you guys what it would look like for HX addition. What would it look like if the reaction arrow had said H2O and H3O plus? We would have had just an alcohol in that position instead. Okay, this is, I should have done the third reaction next, but I'm going to keep these in order. SN1 and SN2 do not happen on aromatic carbons. Instead, we'll actually see a way of substituting aromatic carbons via EAS and NAS, nucleophilic aromatic substitution or electrophilic aromatic substitution. But if we wanted to do SN1 or SN2, we can do that adjacent to the ring on the benzylic positions. For example, this reaction where we introduce water. Water serves as what type of nucleophile, strong or weak? Is water good at donating electrons, or does it wait for something reactive to donate? It's weak. It waits for something reactive. So it has no reaction at the aryl position, but it can substitute at the benzylic position. No reaction to a weak nucleophile. Just because it's a halide does not mean that it will leave in a substitution like any other halide. But at the benzylic position, still reactive. In fact, the benzylic position is quite reactive. And it's because of that conjugation with the ring. Our third reaction is radical halogenation. This is very similar to the carbocation intermediate reaction. When we do radical halogenation, we can either provide the radical halide by illuminating elemental bromine with light, or by reacting NBS with light. NBS is a source of bromine. It's N-bromosuccinimide. And the NBS can't really be used in every place that we use Br2 in light. The NBS works best here at the benzylic position. And once again, we form the most stable carbon radical, which means the most substituted carbon radical. And that's because the carbon radical is in resonance with the aromatic ring, a lot like how our carbocation was in resonance with the aromatic ring. So the radical forms at the benzylic position. I see it far too often that students will see Br2 or NBS, and they'll put the bromine onto the aromatic ring. They'll attach the bromine as an aryl halide rather than a benzylic halide. But I want you guys to recognize that the radical halogenation stabilizes the radical because it's benzylic. It can't be stabilized if it's an aryl halide. It can be stabilized as a benzylic halide by the benzene ring. Most substituted radical forms, just like how our most substituted benzylic carbocation forms. Okay, the third reaction, benzylic oxidation. This reaction will not run unless there is a benzylic CH group. So I want you to notice on that reaction how a methyl, an isopropyl, and a tert-butyl group are all present in the starting material. And the tert-butyl group is unreacted in the product. The tert-butyl group remains tert-butyl, but isopropyl and methyl are completely cleaved. The first step of this reaction requires the oxidizer stealing the hydrogen off of carbon. A lot like how the carbocation is stabilized by the ring and the radical is stabilized by the ring, this also creates an intermediate that is stabilized by the ring. I just don't think that it's the most useful for us to consider the mechanism for this class. I want to demonstrate another example, a way that I think that this reaction is pretty cool. By the way, this reagent I will refer to as chromic acid, although you might recognize that the acid present is sulfuric acid, not chromic acid. This is a source of chromic acid, and there are many sources of chromic acid. You may see potassium dichromate. You may see sodium chromate. And usually these are also written with acid. These are sources of chromic acid. The way that I usually represent this is by writing out chromium trioxide sulfuric acid. Other places in textbooks and on the internet, you will see this referred to as Jones reagent. I don't like it. I don't want you guys to call this Jones, but it's not wrong. I can't mark you off for being right about it. I just think that it tells you nothing. To call it Jones reagent helps you understand very little. Now, I'm not showing you the mechanism because the mechanism is quite convoluted as well, but at least by seeing it's an acidic environment with a bunch of oxygens, I hope that your mind goes to oxidation. I should be putting oxygens into this structure. In this reaction where I have this bicyclic structure, one side is just a 6-membered ring, the same thing happens where I get 2 carboxylic acids in the end. My benzylic carbons are cleaved. What happens to the other carbons? No one knows. No. They just get like charred up. They essentially turn into charcoal or tar. If you guys did the OChem 1 labs here, you might remember we did acid catalyzed dehydration, and we formed this like really dark, thick product at the end once there's very little organic left, and that's just a bunch of charring that happens. All right, my last reaction for you is hydrazine reduction with Metal acid reduction. Oh, sorry. No, they're also named after dead people. Wolff-Kishner reduction and Clemenson reduction. Just call it Jones. Why not? I don't get it. Hydrazine reduction explains exactly what's in the reagents. We're using hydrazine. Hydrazine is H2. Oh man, this thing is going to be the end of me. Hydrazine is H2N, NH2, also written as N2H4. And in basic conditions, it works as an incredible reducing agent. The metal in acid is an amalgam of zinc and mercury with hydrochloric acid. You guys might remember in OChem 1 lab, we hydrogenated fatty acids. We took an alkene and we added H2 across it. And to produce the H2 to reduce it with, we used zinc and hydrochloric acid. I don't always touch on oxidation reduction very heavily in my OChem 1 class. I'm not sure about all of your OChem 1 professors. So I'd like to have a conceptual moment. What's the difference between oxidation and reduction? Take this any way that you want to.
Isn't it something to do with like bonds to an electronegative atom?
Bonds to an electronegative atom, or something more electronegative versus less electronegative? What else? What do you guys remember about oxidation reduction? Mind blank. That's it. You remember the mnemonic from Gen Chem 1?
The one I learned was like oil rig.
Leo the tiger says grr. I like oil rig. Oxidation is loss of electrons. Okay, here's a carbon, a benzylic carbon, and here's that same benzylic carbon. Looks like it has an octet, and it looks like it has an octet. So did it lose any electrons? Then why are we calling it oxidation? Maybe it has lost electrons, but just not in the way that we're used to seeing it. It's not that it's going from 8 electrons to less than 8 electrons, but it's because the carbon has less control over its electrons. And this is where we talk about bonds to more electronegative atoms, bonds to less electronegative atoms. This benzylic carbon steals hydrogen's electrons, steals the electrons from H, and shares equally electrons with all of the other carbons. Then that same benzylic carbon gives up its electrons to 3 bonds to oxygen. It has lost control of the electrons that it stole from hydrogen and control of the electrons that it shared with carbons. So by being bonded to something more electronegative, it has less control of its electrons. A lot of times we'll say oxidation is adding oxygen, although it doesn't have to be oxygen. It can be anything that's more electronegative. And a lot of times we'll simply abbreviate that by saying oxidation is this O in brackets over the arrow. And reduction, we say the opposite way. Reduction is H in brackets over the arrows. Notice how I go from a CHO to a CH3. Carbon was losing its electrons to the 2 bonds to oxygen, and now carbon gets to steal electrons because of those bonds to hydrogen. So carbon has more control over the same amount of electrons. In organic chemistry, oxidation reduction is less about actually giving and taking electrons and more about whether you have more control or less control over the electrons around a carbon. And it's almost always carbon that we're looking at. The Benzylic oxidation is selective to the aromatic ring benzylic position. But did you notice how I didn't call these benzylic reduction? These are significant. They're very useful at the benzylic position, but they are not limited. I just realized I did everything different. What did I mess up on here? I numbered 3 twice, and I didn't give this a number. Wonderful. Not selective to benzylic. Later in the semester, when we get off of benzene ring and we are looking at all sorts of carbon chains again, we will come back to this reaction because it's not something that only is moderated by the aromatic ring. This is something that can happen specifically to an aldehyde or a ketone, but it can happen anywhere. Are you guys okay with me abbreviating aldehyde and ketone there? This is a selective reaction to aldehyde and ketone. We cannot use these reductions on carboxylic acid. We can't use these reductions on esters. We can't use these reductions on amides, but we can use them on aldehydes and ketones. We can use them on aldehyde and ketones anywhere in a structure. For right now, we'll just focus on seeing them here. All right. The final 10 minutes are yours to fill in reagents and predict structures. I'm here to answer questions as you go, and tomorrow we'll pick up with the back side of this sheet. No selective. Who let this guy speak English? Not selective. No.
What? Why?
No. What's the difference between this structure and this structure?
Okay.
It doesn't have an alkene. Yep. Close, but missing something. Oh, that wasn't the part I was missing, though.
Oh, second notes.
Yeah.
You saying it's gonna be like
Yes. Yeah. BR2 itself won't do it, but light initiates it. Mm-mm.
No?
Nope. Yeah. Nope. Close, but if you're assuming it would be something like this, these two starting materials have
Oh, there's a.
right.
Okay.
One has an alkene, one does not have an alkene. HBr won't do anything to, if it's not an alkene, it won't do anything to the alkane. That's it, Esmeralda. Good start. We'll definitely need that reagent in there somewhere, right? But we'll never introduce Br as Br. We can either introduce it as HBr or as Br2, or we can even introduce Br as NBS. Now Br2 with this alone won't do anything. We need to add something else that will initiate the reaction. So if you're choosing this, would you agree that you're saying it's most similar to this reaction?
Yes.
Because this is the only reaction that used Br2. So what else needs to be added with Br2? No, the NBS could be used in place of Br2. Do you know what this is? It is Planck's constant, h, multiplied by frequency, nu, which is the calculation for the energy of a photon. So it's our way of saying light. When you see that HV, that's our way of saying we need to introduce light for this reaction to occur. The light is the initiator. Yeah, Jaylee, when you do your hydroboration oxidation, you'll need to add 1, 2. Otherwise, it reads as mix all of this together. But they actually need to be added in specific sequence. Great work. Yeah, by the way, you may need to rely on that packet of OCHEM 1 reactions from the 2 weeks ago. Not all of the reactions you see here may necessarily come from what you have in front of you. What's up?
Is that right?
Oh, yeah. Yep.
Is this acid catalyzed dehydration?
Is there any other dehydration?
Is it? I don't know.
No, I don't think there is any other type.
Okay.
Well, yeah, there probably is. Like,
Yeah.
enzymes can do anything.
Yeah.
Enzymes can do things that chemists can't.
So is the reagent just H2SO4?
Yep.
Not aqueous? Because aqueous would be.
No, I mean you could put aqueous. That part wouldn't. To me, I don't think that would make the biggest difference. Good to see you, Jan. Looking good. Yes.
Okay, good.
Yep. Perfect.
Sitting over here trying to remember how to put okay, go.
So I will say, if we use H2O and H2SO4, then it should resemble a carbocation stabilized intermediate. The carbocation will go to the most stable position, and that's where water will attack. So acid catalyzed hydration should give a benzylic alcohol all the time. And you don't have a benzylic alcohol there. I'm sorry about the printer. What an annoying thing. And it was like just one side of the sheet. One side was great, the other side was like half printed. Yeah, oh man.
Like on this one, it's not on the side. It's like just a weird portion.
And when I copied it, I went to the darkest density possible, and it's,
Still didn't want to work.
no.
Are you gonna post these answers, or is there an answer?
I don't have an answer sheet for this, but I think maybe at the start of class tomorrow, I'll just draw it up on the board and have you guys fill it in before we start recording. If you'll get up and do it. I don't know, you guys are scaring me. It's week 3. I was thinking you'd be more talkative at 8 a.m. I don't want to say that like a bad thing. I'm glad all of you are here. Last summer, I had like 4 students that came regularly. And who knows, maybe by the end of the semester, it'll be back down to 4 students. I don't know. But I love having so many people. I just need to figure out how to wake you guys up. Take care, guys. See you tomorrow.
So, I'll look at the reaction. Saying, so this will put into 2 things. I know that since this is a phenol, it'll probably react more over here, wouldn't it? Or like, would it still be, would it still be?
Yep. And so now you can see why it says 2 equivalences. It took the alkene and cleaved it,
Oh, for just the one, and then it does it for the other.
and then it doubled. Yeah, because you cleaved that. It's not really a symmetric alkene, but it's kind of a symmetric alkene. Because you cleaved that alkene, you've got 2 equivalences of the same compound. Yep. So this was not a benzylic reaction.
Yeah, 'cause I
It was an alkene reaction.
Okay, that makes sense. Because I was like, if it was benzylic reaction, it wouldn't have reacted. But I guess
And it kind of did, yeah.
yeah, I guess it kind of does.
But it's not the benzylic oxidation because there's no benzylic CH. That alkene had a benzylic carbon, but no benzylic CH. So it's more that it's reacting with the alkene than the benzylic carbon.
Perfect, thank you.
So yeah, I was mentioning you as the one that was on vacation.
Yes, I'm sorry about that.
Oh no.
Do you know we've got 3 Evans in that class?
Oh yeah.
And I still think I was missing an Evan last week. Oh no, I had. Yeah, it was. Yeah.
No
So
worries, totally fine.
thank you for reminding me.
Yeah, of course. But I just wanted to. I went ahead and did all the active homework already.
Great.
Now I just need to do the written one. And then I think that I noticed. I remember you mentioning it, but it's like the choose your own synthesis and retrosynthesis.
The analysis assignment.
Analysis.
Yes. Yeah. So
Yeah.
2 assignments due so far, which is pick a compound and analyze its functional groups and its IR property, its IR predictions.
Okay.
Those are designed, that the IR and functional groups is helped to design to prepare you before the first unit test, because some of that first unit test will have IR, some of it will have functional groups.
That was kind of my other question too, with like the unit test, like because we did some mechanisms and whatnot. So I was sort of, I've
Yeah.
been kind of watching the days that I missed.
Good.
But I just wanted to kind of know like what is best for me to focus on.
Everything that we did in class would be a good thing to focus on.
That's fair.
Yeah. Part A is all multiple choice, and Part B is short answer.
Right.
So Part A, you'll have questions on stereochemistry, mechanisms, reagents,
Gotcha.
and nomenclature. And then in Part B, you'll have questions on like resonance and mechanisms.
Okay.
So it is it's a full span. Yeah.
Right. Yeah. It's real all of Chem 1.
All of OChem 1. And can you imagine if we didn't do that review? Like 2 weeks of review is kind of a lot, and also not that much. Like we skimmed the surface of a lot of stuff because I have to assume that you already passed that class and have that foundation. But I hate making assumptions. And I've had students that come into my class. I had a student that bombed my OChem 1 in a spring semester, wanted to take my summer OChem 2, and I said, you should drop the OChem 2. Or he took my OChem 1 in the summer, bombed it. I said, you should drop my OChem 2, and he said, I'm already registered, I'm fine. I was like, yeah, but you don't really qualify. Like you don't have a C or higher.
True.
And it's really for your benefit to come back and retake it. You stretch yourself too thin. You need to you're not going to do well if that foundation is bad. And he stuck around and bombed OChem 2. So,
There you go.
yeah,
But I mean, I did good in the OChem 1. In fact,
good.
he posted all the grades, which I really liked because I could see my name.
You liked it. I've heard from the students at the bottom too, and they don't like it.
Yeah, I've heard that too. But you still have that working memory, and then as soon as you're done, you're like,
Yeah, that's the difference about Ron's class and mine, I would say, is you can get by in Ron's class by just being really well acquainted for 1 week and then losing all of that material.
yeah.
And you'll see that my perspective of your OChem 1 knowledge is a lot more based in do you understand it than do you remember it. So that might be where you have to
Yeah, sort of.
take everything you learned and like rehash it in a new perspective.
Definitely, yeah. No, I'm definitely understanding now. I'm like, I should take it from John.
Good to see you, Evan.
I took it from 3 different professors. So
For this one,
this one,
Is it-
we're trying to argue.
is it water or is it?
It's not water.
Is it that? Is it hydrogen?
If it's acid catalyzed hydration, you'll get the most stable carbocation, which would be benzylic, and you'd get a benzylic alcohol.
Right.
But we don't get a benzylic alcohol. We get an alcohol off of the other carbon. So it will have to be a different reaction.
It'd be like
No, because you're starting with an alkene and you're going to an alcohol. Oh, I'm sorry.
This one.
Okay, I mean, if you wanted to use like
Oh, I
water
didn't
and
do that
heat.
one.
Water and
Oh, I was looking at
Wait,
this
I
one,
didn't even
Oh, no,
do
you're
it.
good.
Sorry, I don't.
forming the alcohol.
Yeah.
If you wanted to use water and heat, yeah, you could do like an E1 elimination, or use a base that's really good at doing elimination and doesn't really do anything else. Terbutoxide. Yep. Terbutoxide's a great way to do it. Okay. See you guys tomorrow.